501. An ammonia refrigerant brine chiller with a flooded evaporator is shown below. Properties of saturated ammonia are presented on page 29, and a pressure enthalpy diagram for ammonia appears on page 30. Assuming no pressure loss through components, the coefficient of performance of the system shown, with a refrigerant flow rate of 22 pounds per minute, is most nearly what? So they want us to find the COP. Now COP we think of as Q in over W in, or another way to say the same thing is Q dot of the evaporator divided by W dot of the compressor, right? Because the evaporator is where heat is added to the refrigerant and the compressor is where work is done on the refrigerant. And another thing we can do to be a little more specific, we have a pH diagram below which we're going to refer to as we solve through this problem, but just to be really general for a minute and almost as a reminder about what a refrigeration cycle looks like on pH, we have some saturation curve for a given refrigerant, and before the compressor we usually have a saturated vapor or a slightly superheated vapor, and then there's this isentropic compression. So we'll call that initial state, state 1. Then it goes through the compressors, isentropic compression. Now we have a high pressure saturated vapor. We call that state 2. And then we have a constant pressure process by which the refrigerant condenses in the condenser. That gets us to state 3, which is a high pressure saturated liquid. And then we have this isenthalpic process by which the refrigeration expands. So that's a vertical line straight down. So after that throttling process, we'll call that state 4. And then the refrigerant's ready to go through the evaporator and absorb Q in and get back to state 1, and around it goes. So we could say Q in is for the evaporator, W in is for the compressor, and Q out is for the condenser. So if the COP is Q evaporator over W compressor, we could say for each of those that it's M delta H. So for the evaporator, it's the difference in enthalpy between state 1 and state 4. So let's expand that numerator to be M dot H1 minus H4. And we can expand the denominator to be M dot for the compressor, which is H2 minus H1. And now the mass flow rates cancel out, so the COP does not depend on the mass flow rate. It depends on these differences in enthalpies based on the characteristics of the cycle. So even though we've been given the mass flow rate, we may not actually need it. What we're going to go after, and we'll go state by state as we work our way around the cycle, are these enthalpies. So let's go ahead and start at state 1. This is before the compressor. So at state 1, it's the compressor suction. We know the pressure is 38.5 psia, and we know we have 20 degrees of superheat. So if we had no superheat, based on that pressure 38.5, we can use this handy table. Pressure 38.51, that's close enough. We would be a temperature of 10 for a saturated vapor. So with 20 degrees of superheat, it's going to be that 10 degrees plus 20. So T1 would be 10 degrees Fahrenheit plus 20 degrees, would be 30 degrees Fahrenheit. And now we know two things about that state. That's enough to spot it on the chart, and we should be able to grab H1. So let's go ahead and do that. Okay, so zooming in, 38.5 is just below 40, and 30 degrees, that brings us to about right here. And now we want the enthalpy, so I have to zoom back out. So we need a line vertically straight down. Vertically straight down, I'm going to say that's about 620. So H1 equals about 620 BTU per pound. Okay, now we can jump to state 2. For state 2, we know that it gets there by the compression process, which is isentropic. So we can say S2 equals S1. S1 because it's constant S, isentropic. And we also know it's now at the high pressure condition, which we were given as 229, so P2 equals 229 psi. And I actually don't care what the entropy is. I only care that it's a constant entropy process so that I can follow a line of constant entropy from state 1 to state 2. So this is without actually even looking up what this number is. We're not going to do it on the table, we're going to do it on the diagram. So let's go ahead and do that. We're going to go from that state 1 point along a line of constant entropy, which are these lines here, these sort of slanted curves. And we want to go all the way up to 229. 229 in terms of pressure will be somewhere along this horizontal line. So if I follow a constant entropy line up to there, that might get me to about right here. And I realize that's a curve and I'm drawing a line, so it's imperfect, but we'll do the best we can. Now, what would the enthalpy be at that point? We need to go vertically straight down again. Hopefully that's roughly vertical. You may be able to do this more accurately on a piece of paper with a ruler, but I'm getting about 740 BTU per pound for state 2. So this is state 1. This is state 2. So let's record that. H2 equals 740 BTU per pound. All right, so we have H1 and H2. Now we need H4, but we have to continue around the cycle. So we'll work on state 3. The process from 2 to 3 is a constant pressure process as it goes through the condenser. So we can say P3 equals P2, which is still 229 psi. And we also know in the condenser, all of the refrigerant condenses such that we end up with a flooded evaporator, as they said in the problem, or basically we're making the assumption that it's a saturated liquid with a quality of 0. So it goes all the way to the left side of that saturation curve. So it's fully a saturated liquid. And if that's the case, we can actually use this chart for pressure 229. What's the enthalpy of a saturated liquid? So let's go along the left, find pressure 229. That's pretty close to this guy. And a saturated liquid would have an enthalpy of 161, which is nice, so we don't have to do another lookup on that diagram right now. We can just record that. H3 equals 161 BTU per pound. And now state 4, the process by which we get from 3 to 4 is the expansion process, which is isenthalpic, constant enthalpy. So H4 equals H3, which equals 161. So now we have H1 and H2 and H4. So we can find the COP. And I'll spare you the units since they're all BTU per pound. 620 minus 161 over 740 minus 620. COP equals about 3.825, which is answer choice C. So to summarize, we start with what we have at the compressor suction, and we work our way around the cycle using what we know about each process in the refrigeration cycle, what remains constant. And as long as you have any two things, whatever they are, whether it's pressure, temperature, enthalpy, entropy, you work your way around and figure out what you need at each state and then use that to solve for whatever they're asking. It's a very common process that you work through for different problems where they could be asking for different things. And there's no other faster way other than to just work your way around the cycle and define each state and then solve.